Hello, my friends. Cynic here. I'm Nick, and I'm going to be talking you through the first video on Physics Paper 1 for AQA, which is the topic of energy.
And in this, we'll be considering first a definition of types of energy and energy stores. We'll then look at energy examples through kinetic energy, through GPE, gravitational potential energy, elastic potential energy, and thermal energy, specifically with this wonderful term, specific heat capacity. We'll then look at the rate of energy transfer in power. We'll look at examples of energy transfers and something called dissipation. We'll look at how we can calculate the efficiency of energy transfers and improve that. And finally, how we can generate electricity through use of energy resources and where we can get that from. So the first thing that we really need to do here is look at what energy is and the words that we're going to use when we're describing it. So we're going to use the words system and store really to describe energy. And a system is just the system that we're considering when we're looking at the energy change. So we might want to look at the energy change in a whole kettle. We might want to look at it for a catapult. We might want to look at it for the whole world or the whole universe. But whatever we're considering is the system. So we define it as an object or a group of objects that we're considering and looking at the energy transfers and changes within. And energy itself is usually stored. So it's stored in a different way, and when the system changes, the energy is transferred to a different type. So if you imagine this catapult, it's an object being projected upwards. It has kinetic energy as it's moving upwards, and as it is moving, the system, the object that's actually being fired, is losing kinetic energy and gaining gravitational potential energy. So that's a transfer that's happening when the system is changing. Water boiling, you're putting in heat and the particles are going to get hotter, so they're going to gain more kinetic energy as they move around more. An object that's accelerated by a force is getting forced. As it gets pushed, it's going to be moving, so it's getting a transfer of energy. As it's moving, that kinetic energy is going to get transferred to heat by friction. A vehicle slowing down, again, it's got kinetic energy. It applies its brakes, and the brakes will cause a transfer of kinetic energy to heat. So all of these are a system changing, and so the type of energy that it has, the store of energy that it has, is also going to change. And that system can be changed by three things. These are the things that AQA wants us to know. And that's either by heating, so the system will be gaining energy through being heated. Work will be done to it by a force, or work will be done to it when a current flows. So this is for electricity, and the force is obviously a force, a push or a pull on that object will cause work to be done to it, either causing it to gain kinetic energy store, or maybe heat store if the kinetic energy leads to friction, that sort of thing. The types of energy that we need to consider and that we need to be able to name, we'll look at a few of these in a minute. First is kinetic energy. We've then also got gravitational potential energy. We've got elastic potential energy, and we've got heat. But the main other one that we might look at is chemical energy. But these first four are the ones that we will really work with. Anything else can really kind of be banded into those groups. The other types that you might not consider so much in this topic, but in the wider element of physics is quite important, are magnetic energy, which is more a potential type of energy really, and internal energy we'll look at in the particle model of matter topic, and finally nuclear energy. The first type of energy that we're going to look at is kinetic energy, which is just the energy of a moving object. It's how much energy it has when it's moving, and it can be defined as its equation, which is big E with a little k next to it equals half times by the mass of the object times by the velocity that it's travelling at squared. So the components that will affect how much energy it contains are obviously its mass, but the velocity is going to have a much larger impact because it's a velocity squared. An example exam question here is this is from AQA paper. A cyclist of a mass of 80 kilograms, speed is 12 meters per second. Obviously speed here is velocity, same thing in this equation. So if you write out the actual equation you need to use, that's the first mark that you're going to get usually. You write out the equation, then we write it out again, but substituted. So EK is what we're trying to calculate, equals half times by the speed, which is times by the mass, which is 80, times by the speed, which is 12, but squared. You put that into your calculator and you get your answer. Job done. Life is good. The other thing that can be tricky with this equation, though, is rearranging it, though. So quite often you can be asked to work out the velocity of the object based on the energy that it has and the mass, and the energy sometimes we get given and need to calculate the gravitational potential energy of the object if it's falling and convert that into kinetic energy, because it's turning its potential to fall into movement. It's gaining kinetic energy, and we can use that energy then to calculate the velocity, and we'll see an example of that later. But if you're going to rearrange this equation, just as you would rearrange any other thing, we have to move different functions to different sides of the equation. So in this case we want to move the half times by mass to the left hand side, so we would do the opposite of its function here, which is divide by. So EK divided by half m equals the v squared, but we haven't solved the problem yet because we've still got v squared, so we need to square root both sides, which gives us EK over half m square rooted equals v. And the reason I say no triangles, I don't like using triangles in physics, because you do have a lot of three-part equations where you have distance, speed, time, and you can quite easily then do distance divided by time times by speed, whatever, in a triangle, and you might have learned those in Key Stage 3, but they just don't work for some of these longer equations, so try and avoid using them and try and rely on just actually rearranging equations and developing that skill instead. The next equation that we need to look at in type of energy is gravitational potential energy. So this isn't actually a movement energy or anything like that, it's a store, it's a potential energy. It will get released if the system changes. So the potential energy stored here is based on its height and its weight. So the equation that we end up giving is EP, which means energy potential for gravitational in this case, is equal to the height times by its weight, and weight is equivalent to its mass times by g, which is the gravitational field strength. So height here must be in meters, mass must be in kilograms, and g on Earth is it's 9.8, but it's measured in meters per second squared, or it's measured in newtons per kilogram. But that is usually, as I say, on Earth 9.8, and that's the number that we need to actually learn, that g is 9.8 on Earth. Quite a lot of the time you get given it, but it is part of the content you need to learn as part of the forces topic later, so it's worth knowing now. Why not? So if this object is dropped or released, this gravitational potential energy will convert to kinetic energy as it falls. Now bear in mind, gravitational potential energy is something you gain as you move away from the centre of the gravity of the object. So everything has GPE on Earth's surface, but we're looking here for the change in height. So as you change its height, how much energy is released as it does so. And as I say, that energy released is dependent on the mass and the field strength that is within. So if it's dropped, it's going to release that energy as kinetic energy as it falls, and so the object will be gaining acceleration because it's gaining kinetic energy. So if we have a bungee jumper, I was going to go over a bungee jumper, but it's a bit more complicated, so I've drawn a lovely little parachutist now instead, so ignore that a little bit. We'll go for parachutist, and if he jumps out of an aeroplane, he has a mass of 50 kilograms. Let's say that he's fallen 50 meters. We can quite easily find out his change in gravitational potential energy. So EP equals h times by m times by g, so we write it out, we then substitute in what we know. So he's fallen 50 meters, he's got a mass of 50 kilograms, and gravitational field strength is 9.8, and we get 24,500 joules. Of course, energy is measured in joules. A common link then to make is, if this person is losing 24,500 joules, how much energy of that is going to get converted to kinetic energy? Well, in an ideal world, it would be 100%, so 100% of that would get passed on to kinetic energy. But of course, in a true world, we have factors like friction, we have air resistance, we have drag, same thing as air resistance. They're going to cause objects to be slowing down as soon as they start speeding up, or countering that force, and so releasing kinetic energy instead, converting it into heat. So in this second question, the second follow-up exam question here, we're told that 80% of this change in GPE is converted to kinetic energy. We need to work out how much kinetic energy he has gained by falling 50 metres. So we'd take that 24,500, we'd multiply it by 0.8, which allows us to then work out how much it's changed, which in this case he would get 19,600 joules of kinetic energy. And the next step from that would be then to calculate his speed. So we talked earlier about how we can use the equation to do that. So you'd use v equals square root of ek over half m, and if you substitute that in, we've got square root of 19,600 over half of his mass, which is 25, and that allows us to work out what speed he would have. And in this case, it would be 28 meters per second. The third type of energy we need to learn about is elastic potential energy, and this is the energy that's stored within a spring. This is, though, based on the assumption that the limit of proportionality is not reached. Now that is a term you need to know, limit of proportionality, and this is just where the spring has been stretched so far that it will not return to its original length. So I'm sure we've all done this before. You've got your lovely tightly coiled spring from your pen, because you all love taking apart pens, or you've got your slinky, and you stretch it so far that when you let it return to what it should be, it ends up kind of looking like this. And that's where it's gone beyond its limit of proportionality, so it's broken the law of how it should work as a spring. Now the equation that we use, now we're given this one, we need to learn the previous two for kinetic energy and for gravitational potential energy, but we're given this one, and it's EE, so it's given on your equation sheet, equals half KE squared, where E is the extension in meters, K is a spring constant in newtons per meter, and this is obviously in joules, it's energy. So the spring constant there, we can talk a little bit more, it's based on the type of spring that you're using. Every spring in elastic material has a different spring constant. In fact, all objects have a spring constant of some sort, and it's the force needed to extend that spring or that object by a meter. No, you're not always going to be able to extend a spring by a meter because it will go beyond its limits of proportionality, but that obviously can be scaled down. So that value is there. You'll sometimes have to calculate the spring constant, you'll have to sometimes calculate the elastic potential energy in it, you sometimes have to be able to rearrange this equation, which works just like for kinetic energy, where you've got this weird square rooting part that you would need to do to find out the extension. But if you've got a simple setup here, an exam question again, we need to find out the elastic potential energy in a spring that's stretched by 30 centimeters with a spring constant of 400 newtons per meter. So if we substitute those values into our equation, we get half times by spring constant, which is 400, times by the extension, which is in centimeters. So we need to convert that into meters to match our equation here. So you must have it in the right value. So 30 centimeters into meters is 0.3 meters. And if we multiply all of those together, I've made a mistake, I haven't squared my extension. There we go. If we multiply all of those together, we get the answer of 18 joules. The next part of energy that we need to know is the thermal energy component, and we need to look at something called specific heat capacity. Specific referring to the material, heat, obviously how much energy can get put in this case thermal energy, and capacity, how much it can take to change its temperature. So the definition, it's basically defining the point that as an object's temperature changes, the energy within it will change too, and how much it changes by, how much the amount of energy changes by as an object's temperature changes, is what we call the specific heat capacity. So you can define that as an equation as C, which is specific heat capacity, is equal to E over m, the mass of the object, times by this symbol here, which is theta, which means change in temperature, and it's technically change in energy there. But you're given this equation, and you're given it as delta E equals mc delta temperature. So change in energy is joules, mass is in kilograms, C is in units of joules per kilogram degrees C, and temperature is in degrees C. Now this is a required practical, so we need to be able to describe how to calculate specific heat capacity, and so let's get to it. So the equipment that you'll need is shown below. You'll have to have firstly this immersion heater. So the immersion heater is sat inside the material and it's next to a thermometer. So the immersion heater will cause the material to heat up, and the thermometer will tell us how much it heats up by. The thermometer should be sat in oil, and it means that you get better conductivity between the actual thermometer itself and the material. So it's not just measuring the temperature of the air around it, which remember is quite a good insulator, it's measuring the temperature of the actual metal or the material, whatever it is. The immersion heater will have a certain power supply to it, and that power supply will make it get hot. It's got a high resistance, so it gets hot, causing the material to get hot too. We should encase it in insulation. The insulation is there to prevent heat loss to the environment, so that the heat coming from the immersion heater is going directly into the material and not to anything else. If you do lose heat to the environment here, the accuracy in the data that we collect would decrease. So with this part of the setup we've just looked at, we can know the change in temperature through the thermometer, and we can know the mass of the material. But the other part that we will need to be able to work out the specific heat capacity, so we've got the mass, we've got the change in temperature, we need to find out the energy change. And to find out the energy change, we can go down one of two routes. The first route is to use a voltmeter and an ammeter. So the voltmeter, as you'll see from the electricity topic later, the voltmeter is plugged in parallel over the immersion heater to find out how many volts, the potential difference across that immersion heater. And the ammeter is in series to show us how much current is being passed through the immersion heater. And using those, we can use the equation P equals IV, which is from your electricity topic, to work out the power that the immersion heater is using. So you multiply your current and your voltmeter readings together and you get your power. And with that power, we've got the equation power equals energy divided by time, which will come out later in this topic and in electricity. And if you rearrange that to give power times time, you can multiply how long we've used this immersion heater for by the power that the immersion heater is using to give us our energy. So that actually, for this setup, you also need to have a stop clock to find out how long you've been doing the test for. The alternative route is a lot more simple, is using something called a joule meter. And the joule meter, rather than deleting that, Nick, let's go for this, that's much better. If we use a joule meter, it just tells us how much energy the power supply is putting through. You can also do that directly for the immersion heater, and that just straight up tells you how much energy is being used. So it's a much simpler way of using this experiment. However, for pathway number one, using power and everything, do be aware of this method. Do know this technique of calculating the energy used, because it's a fantastic crossover between this topic and the topic of electricity, and they do like to cross over between different topics in papers. Okay. With required practicals, we need to consider terms like valid. So when you're writing a 6-mark question, for example, and they ask you to describe the method for 6 marks, they might say, include how you're going to make this method valid, or make sure the outcome is valid. And valid means that the methodology is going to allow you to have a conclusion which is supported by an appropriate method, accurate and precise results. So in this experiment, there's a few things that we can do to improve the accuracy. The main thing we need to do is take repeats, so repeat readings, so heating this all up, timing how long it takes, or calculating the energy that's being put through it, letting it all cool down, and then doing it again. So repeating it and calculating a mean. Don't just say calculating an average, calculate a mean. You could say calculate an average in brackets, a mean, but remember there are different types of averages, so it's important to determine which one you're going to do. The second thing that we could do is to keep the temperature change that you're looking at a small change. So don't kind of heat this up from 20 degrees to 100 degrees. Do it for a small change, so maybe 10 degrees C change, and you could time how long that takes, work out the energy that's gone in, and onwards from there. Because the complication that you'll face is that once you're heating it to 100 degrees, there's a big difference in temperature between the actual material and the surroundings, and so you're going to lose heat a lot more quickly, and so the accuracy will drop. So a small change in temperature. And the other thing that you can do the final thing I might ask for is safety, and in this experiment you're getting a material very hot, potentially super hot. The immersion heater will get hottest first, and then the material around it. So obviously it's just simple as saying avoid touching the actual the heaters, let it cool down first, do it on a heat-proof mat, that sort of thing. So that's our examples of energy looked at. We're going to now look at what power is, and power is the rate at which energy is transferred, or the rate at which work is done. Essentially the same thing. It's the transfer of energy or force being applied, and so work being done to an object. So it's the rate at which how quickly that is done. So whenever we have rate, we must consider time. So it's going to be whatever we're looking at divided by time. So power is equal to the energy transferred over time per second, so joules per second. That would be in joules, and this would be in seconds. Or the other definition, as we say, is work done divided by time. The only difference in work done and energy transferred is that work done is always to do with a force being applied causing an object to move a certain distance. When you look at the force topic in paper 2, you'll see that the work done is equal to the force multiplied by the displacement of the object, how far it's been pushed. Now you may well be asked to define power by giving an example of an experiment, or you're given an example of an experiment and you need to show how it explains what power is. This is a typical setup that you would find. So you've got a motor here which is pulling a bit of string, which has got a pulley, and around that pulley it's pulling up a set mass. Now how we would define power here is the time it takes for that mass to be pulled up a certain distance. If you consider this being done twice, you've got a motor that works with a power of 1, then it works with a power of 2. The difference would be that the energy or the work done is exactly the same, because we're moving it with the same amount of force and the same amount of distance. The force that's countering here is obviously weight. So we're countering that weight with moving it a certain distance, which is just the same as it was before. But the difference that you would have with the different powers, this one with the power of 2 would be twice as fast. So it would move it up that distance twice as fast. And that's really how you would define power. So you've got the same setup, but one that was twice as powerful would move the object up twice as quickly. So the time it takes would be half as fast. So if you put this into an example, P equals E over T, you could call E 100, and T for the really fast one would be 1. Whereas if you had the same setup the other way, the energy required to move up that distance is exactly the same, but the time taken is twice as long, so the power ends up being half as much. So with the rate of energy transfers considered through power, let's look at how energy transfers can happen. So they can either be useful transfers, so transferred usefully, so getting the energy transfer that we want out of it. So a car motor, for example, will try and get kinetic energy out from the chemical energy stored that it had as fuel. We could also have energy being stored. So if you're lifting up an object, that object is gaining gravitational potential energy in its store, or the energy gets dissipated. And dissipated means it's almost been lost. It's gone to the environment. So usually this is as heat or sound. That's something that then will dissipate. It will spread out until it is negligible. And negligible means it's so little that you wouldn't even notice it. So if I was to turn on Bunsen burner in my lab, that heat would be felt quite close to that Bunsen burner, but if I walked a mile off in a distance, I wouldn't even notice that there was a Bunsen burner lit, because the heat has dissipated so much, it's spread out so much, it won't be noticeable. There is a really important rule here for energy transfers, and that's that energy cannot be created or destroyed. So we cannot magic up energy out of nothing, and we cannot destroy it and make it disappear. all the energy that we have in the universe was there at the start of the universe, and it will be there until the end of the universe, there is going to be no net change, no overall change, no total change to the total amount of energy. This, of course, only applies to a closed system, so where there's no way that the energy can leave a system that we're looking at. So if you imagine a kettle, you can't really make a kettle a closed system because it's going to heat up the environment around it. So a lot of this is kind of theoretical for a closed system, but when we're talking about the universe, no energy can be created or destroyed. It must just be transferred into a different store of energy. And relating to this, to help us to prevent producing what we call unwanted energy transfers, or to cause energy to be dissipated, causing what we might say to be wasted energy, we can reduce unwanted energy transfers by doing things that will counter things like friction or heat loss. So countering friction, we could lubricate things, lubricating the joints between two parts so that they're going to cause less friction and cause less heat loss as a result. And also we could prevent heat loss if we wanted that to be happening, or to be not happening. We could use thermal insulation. And thermal insulation, a really good example of that is used in houses, and they could ask you about this too. So we want something that's got a low thermal conductivity to be our insulating material, and the larger the thickness of that, the better an insulator will be. And if you're doing physics, there's a physics-only required practical here where we need to look at the insulation. So you may well have in class had a beaker or something that you coated in insulation, and you looked at the rate of heat loss over time. So this is a rate of heat loss, so rate of temperature change, or rate of theta as we know now. So that's the change in energy over time. And it's really nice practical to do because it's very much following your common sense, but they can ask you about validity and safety here once again. So validity would be things like taking repeats, making sure that you're controlling variables. You've got the same amount of water, for example, because if you have more water, it's going to take longer to lose heat. If you've got less water, it's going to lose the heat more quickly. Things like that. So it's a lovely little experiment, and you can watch my video that will be coming soon about required practicals and some of these key terms in how science works at some point soon to find out more. Now, these energy transfers will have something called as efficiency associated with them. So that's how efficient the energy transfer is from the energy that we've input compared to the energy that we get that was useful output. So we're looking at forming a ratio of the useful energy output compared to the total energy input. So if we write that as an equation, this is one we need to be able to know. It's useful energy output divided by total energy in. And that gives us our efficiency. Now, you could be asked to calculate a percentage efficiency. This here would give us a ratio. If you wanted to work out a percentage efficiency, you just do 100 times by that, because technically with the one before you get a decimal, and we're multiplying that by 100 to give us a percentage. But in the specification, we just need to know the ratio part. There are technically two equations that we can learn here. One is the useful energy output and one is the total energy input. You could also talk about it in power, so useful power output over total power in. Essentially it's the same thing, because the energy is going to be dependent on the time that you're using it, and the total time is going to be equal to the amount of useful time that you're getting out, if you like. So it's the same setup. Useful divided by total divided equals efficiency. Very lovely little setup. And for higher tier here, we've got a little link again to increasing the efficiency of energy transfers, which really goes back to what we said in the last little bit on energy transfers, that we can do things like lubricating to prevent friction, preventing heat loss through insulation, trying to make sure that the majority of the energy that we put in comes out as useful energy. So for example, solar panels at the moment, we've got a real push on trying to make them more efficient, so turning the solar energy that they absorb into useful electricity output, and that's getting better with time. The final part of the energy topic is looking at different ways of generating electricity using natural resources to allow us to do so. We don't need to know anything about how they actually work. It's more to do with the advantages and disadvantages, how useful they are. The first category of resources that we'll look at are non-renewable. So these, in short term for our use at least, will eventually run out if we use them in high quantities. And these are coal, oil and gas, which are fossil fuels, and nuclear fuel, which is things like uranium and plutonium that are used in nuclear reactors. And the problem with fossil fuels, as you probably know, are the production of greenhouse gases like CO2, and sometimes things like sulfur dioxide, things that will crop up in when you're looking at chemistry and pollutants in the later part of paper 2. And these are really harmful for our atmosphere and for leading to things like climate change and acid rain. Not good at all. Obviously they'll eventually run out and we have to mine for them quite a lot of the time, mining or drilling, using things like oil rigs. So they're pretty harmful to the environment. They're really not very good for us to be using, but they're handy because you can stick some of these into cars, for example, to make them run, so they're easy to carry around for transport. So there are many advantages of using them, and we have a lot of them stored up, but as I say, for the moment, a lot of the negatives probably outweigh the benefits. For nuclear fuel, again, it's non-renewable, but we have a lot of it available. The way that it works is for a controlled nuclear fission reaction, and again, this is a great little tie-in to the atomic structure topic, which comes later in this paper. So they could talk about what the advantages and disadvantages of nuclear fuel use are, and then you can say what nuclear fission is. Generally, it's good because it's fairly safe. Obviously, there have been disasters in the past, but it's fairly safe. We can get a lot of energy out of little mass. We don't need to put much in. It's fairly expensive to get it all set up and running, but once it is, it's pretty good. It's reliable. So we can have it running when we want to. We can adjust how much power output we get, but it does have negatives because we produce toxic waste, which is radioactive, which we need to store somewhere, and obviously there is the slight risk of a meltdown, which is pretty dangerous. But as I say, they're fairly safe. It's unlikely to happen. The reliability is an important concept and idea for fossil fuels as well. Of course, if we are all needing to make a cup of tea at the same time, we can increase the output of power for a fossil fuel power station by just burning more of them. So they are very reliable. We can use them rain or snow or sun, whatever is happening, and it's no problem at all. The second group of sources of energy are renewable. So from biofuel, wind, hydroelectricity, geothermal, tidal waves, the sun, they all are renewable, so they technically shouldn't run out in the short term. There are a few things you could argue, like the sun is not going to be around forever. Fair enough, but in our short term, they are renewable. They're going to replace themselves, or we can make more of them, or they're not going to run out. So biofuel's the first nice one. Biofuel works very similarly to fossil fuels, however we can produce them ourselves. So we take plants, we produce, we grow sugar, for example, we ferment that to make alcohol, and that makes a lovely thing that we can burn. Very similar, it produces heat. The heat causes steam to be formed, steam turns a turbine, makes electricity. Simple. Wind, again, wonderful thing. Wind is just going to be around. It's not necessarily reliable, because it's not always windy. We have to have a certain amount of wind for the wind turbines to be able to work, and you could argue that they're not very good to look at, so they are kind of polluting our horizons, if you like. People don't really like them, but out in the ocean you could argue no one's going to be able to see them. They work great. Hydroelectricity is based on gravity pulling water down, so it's a transfer of gravitational potential energy into kinetic energy, which turns the turbine, which turns into electrical energy. That gravitational potential energy store is quite a good one because the evaporation of water is doing it for us. It's raining down into lakes, into mountains, into rivers, and as it falls through dams, for example, there's a little turbine that gets spinned. Reliability wise, as long as those reservoirs have got water, we can be generating electricity. It's great. Geothermal is based on us taking heat from underground, deep underground, where there's lots of warmth, and that warmth can be used to generate steam. Steam again can turn a turbine. Is it reliable? Yes, we've always got heat down deep underground, and the tricky part is the drilling down into there. It's just fair enough. Tidal is, again, looking at how oceans will rise and fall with the tide, or the coastal parts of oceans will. And what we can do is we can trap that water and force it to move air through a turbine. Is it reliable? Well, we know when tides are going to change. Tides are always going to be changing in certain parts of the world. You just have to collect the electricity from it. And wave power, just the same. You could argue it's not very reliable in this case because we don't always have waves, but out in the ocean, far out in the ocean, we always do, and it's going to be variable day on day, but easy to harness all the same. The only one that's not going to be using turbines to generate electricity here is the sun, and the sun is using solar panels. And again, are these things reliable? Well, we technically know when it's going to be sunny in the daytime, but is it going to be cloudy? Are these things very efficient? Things you could debate. So there's a lot of considerations you could make for all of these different resources, and it's worth having a balanced view of all of them. And you've just got to make sure that you look out for this keyword evaluate, because when they want you to evaluate something, you need to give the pros and the cons, so both sides of the argument, and use your knowledge and whatever data they give you to support that. That's probably the most important part of what they'll ask you to do, and the most common part of what they'll ask you to do here.
Thank you for watching. That's the end of our video on energy, following and working through the specification. If you have any questions, please leave them in the comments below. Please do like and subscribe and check out the other videos I have.